So let me start today's lecture 8. So lecture 8 is particularly important because we are now solving the Poisson equation in its full consistent way. So now we solve a Poisson equation and consider the contribution from electron, which is assumed as this, and whole contribution. Of course, in our example, we will neglect the whole contribution only because in this system actually we have no holes, no meaningful number of holes, but in principle we can consider both of electrons and holes. So compared with our previous lecture contents, which is really based on a linear system, I think that we have a big jump into non-linear systems. So in my opinion, although we have not many slides in today's lecture, but achieving the goal of lecture 8 is quite important for your future progress. We are more or less working in exercise style lecture today. So now we have sufficiently prepared for solving the Poisson equation with electronic contributions. So this is typically called non-linear Poisson equation. So in this field, the Poisson equation with the electron density, which is non-linearly dependent on the electrostatic potential, is typically called as non-linear Poisson equation. So let's just solve it together. So this is the residue of isentry. So residue vector can contain many different entries, and typically it has large n entries. So let's say that this is n, capital N by 1 vector, and here we have a certain first term and the last term, and in this specific example we have a certain first a few points assigned to silicon dioxide, and final a few points also assigned to silicon dioxide, and in between we have some points assigned to silicon. In the case of regions which are devoted to silicon dioxide, actually we don't have to consider the contribution from electrons. So it's okay. And now we have to think about the silicon region. So in this case, we have to consider the electron contribution. And only difference is compared with the previous one. Previously, we had the terms related with Laplace equation, and this is corresponding to doping concentration, and that was all. However, today we have to consider the contribution from electrons. So please note that once again. Please make a comparison between this doping term and electron term. here we have the common factors like delta x and q, delta x and q. So their magnitude are simply acceptor density and ni exponential phi I over vt. So you know that usually this can be, for example, 10 to the 18 per cubic centimeter, 17 or 19 per cubic centimeter. This is typical numbers for our doping density. M and I at 300 Kelvin is just 10 to the 10 per cubic centimeter. So if our potential is close to 0, then this exponential term will give us a number quite close to 1. So this acceptor density is much larger than electron density. So that's the reason why we have neglected the electron contribution in our previous lecture. But if the potential is sufficiently large, then maybe we can have a certain situation of electron density now becomes comparable to the acceptor density, or even for larger values we can have larger electron density than the doping density. That's the reason why we have to consider electron contribution now. You can easily expand our discussion to bipolar cases where both of electrons and holes are considered. Okay, so since now we have the residue vector written here, we can easily construct the Jacobian matrix. So the component of Jacobian matrix is quite easily obtained by taking, for example, this I, I plus 1 term is given by round Ri over round phi I plus 1. And as you can see, here we have a partial derivative with respect to phi sub I plus 1, and the newly added term really depends on only phi I. So this one, this red colored term, does not contribute to the Jacobian matrix in additionally. So here we have no contribution. So it is quite easily understood. And here also we have here j sub I comma I minus 1, also no contribution. Only the diagonal component I comma I has some contribution, a contribution from this diagonal term. And when we take the partial derivative with respect to phi I, it simply gives minus delta x q and I and q kbt exponential q phi I kbt. I just took the partial derivative with respect to phi I, so I just have the same function, only difference is this coefficient of phi I is in front of exponential function. Then, as I told you before, now we have the contribution from whole. It is written as minus q phi I kbt. So if we have this blue colored one from holes, then what will happen to our Jacobian matrix? What will happen to the Jacobian, so for example, j sub I comma I component? Maybe we have a certain term, but how does it look like? So this is electronic contribution, and whole contribution when we write down, then this is also delta x q and I q over kBt, exactly same as the electronic one, exactly same, and only difference is related with this exponential function. Exponential term has minus and the same argument q phi I divided by kBt. So then let me just think about the sign of these three terms. The sign of these three terms is like this. This is always positive, and this is always positive, and this is the j sub I comma I, the diagonal term is always negative. So if we consider the terms related to epsilons, that will become 0. Then how about the entire sum? When we consider this one, is there any relation between the sum and 0? So this one becomes always smaller than 0 because these two electron contribution and hole contribution both contribute negatively. So I wanted to summarize. In this case, in this nonlinear Poisson equation, we can find a very significant feature of our terms in Jacobian matrix. So first one is sign. In its sign, diagonal component j sub I comma I and all other component which is called as a non-diagonal component have different signs. I mean that if this is negative, then all other non-diagonal terms have positive sign. That is the first one. So you understand. The second one is under the assumption of this sign constraint. Now we can think about this one. Absolute value of j sub I and the sum of all other non-diagonal component. Then what will happen? In this case, even the diagonal component's magnitude is larger than the sum of all other non-diagonal components. So now you can write down this way. So these two conditions, so always diagonal component has the opposite sign to all other non-diagonal term, and its magnitude is larger than sum of all other non-diagonal terms. So we call it as diagonal dominance. So diagonal term is dominant over all other non-diagonal terms. You will think about why professor stress on this point. So seemingly quite arbitrary, and happen to be we have certain properties, but these properties are quite important. So diagonal component has a sign which is distinctively different from all other terms, and its magnitude is always larger than others. Please remember these two conditions. So this is really important conditions for our application. Okay, then anyway, now our matrix has quite good properties of these two conditions, and now let's go to the real implementation. So compared with the previous Poisson equation under the depletion approximation. The only difference you have to introduce in this lecture is to add this Jacobian component and of course this residue component. But point is, since now your residue and your Jacobian matrix really depends on the phi sub I, the temporal solution of your Newton iteration. So you have to evaluate your Jacobian matrix every time you solve the Newton-Raphson method. So that is really big deal. If we can use or if we can reuse the Jacobian matrix, then everybody will happy. But unfortunately, since we have the nonlinear system, so Jacobian matrix should be recalculated every time. So that gives us a certain overhead to recalculating the Jacobian matrix. So let's go to our example. So here we have the first part of our example, and we just define many quantities. For example, this is a Q, you understand, epsilon naught, you understand, also Boltzmann constant, and temperature. And thermal voltage is assigned, and we have now used a 0.1 nanometer spacing for our discretization. And here we have 61 point. It is only because we have assumed that our oxide thickness is 0.5 nanometer and silicon thickness is 5 nanometer, and we have another oxide, so here we have another 0.5. Yes, that's the reason why we have 61. And if we have, for example, 0.8 and 0.8, then eventually we will have 6.6 nanometer thick structure. So by assuming the delta x kept as before, then we have to have n, large n, equal to 67. And that is just a trivial thing. Then also we can define the position x. The position of our interface, first interface, occurs at 6th position and 56th position. You can easily change it to different values. And relative permittivity is 11.7 and 3.9 for silicon and oxide. Also, here we have doping density corresponding to 10 to the 18 per cubic centimeter, and Ni at 300 Kelvin is simply given as this number, and here we have a certain coefficient, frequently appearing coefficient. You don't have to explicitly define it or not. So these are all defining certain variables. And let's go to the inside of our Newton-Raphson iteration. So first, residue vector is cleared and Jacobian matrix is cleared. Residue vector is n by 1 vector and Jacobian matrix is n by n matrix. And we have to introduce certain boundary conditions, and boundary condition here, the boundary condition for our first node, and this is the boundary condition for our last node. If we write down in this way, this means that R1 equal to phi 1 minus 0.33374, and we wanted to make it 0 eventually. So our goal is to set phi1 equal to 0.33374. And if we are considering non-zero gate voltage, then what should we do? In this case, instead of this specific number corresponding to the zero gate voltage, for example, we can write down in this way. Then, if we solve it, then we will have phi1 equal to 0.33 plus applied gate voltage. That is more generalized way to apply the boundary condition. Same holds for our R sub n. In this case also we can apply phi n minus certain number boundary value should be 0. That is our goal, and we apply the certain value directly to our boundary variable. And since now we have R1 equal to phi 1 minus a certain number, so the Jacobian matrix component can be immediately calculated. For example, taking round R1 over round phi 1, we will have just number 1. So this one contribute to number 1, and all other components R1, phi 2, 3, 4, 5, they are identically 0. So round Rn over round phi n give us 1, and all other phi numbers like phi 1, phi 2, phi 3, that will give us just 0. So this is enough for our boundary conditions. Then this is just boundary conditions, so we just touch it, R1 and Rn. How about the intermediate values starting from R2 and ending at R sub n minus 1? We have to impose the Poisson equation into them. So that is done in the next slide. And this next slide, we are considering the Laplacian or Poisson part. So this is related with the second order derivatives. And since we have different materials, we should be a little careful. So this first if statement just says that purely oxide resin, and this the last case is corresponding to purely silicon case, and in between we have two boundary values corresponding to interface 1 or interface 2. In this case, we have to mix epsilon sub silicon and epsilon sub oxide, because we have just a mixture of silicon and the silicon dioxide in these interface points. I think that you have already done it for your previous homework, so we don't have to repeat it again. And now the difference for lecture 8 actually appears in this slide, the charge part. Previously we had just a charge part for our acceptor density. Previously we had only term related with acceptor density, and that does not contribute any further component to Jacobian matrix, because this is just a constant, and when we take the partial derivative with respect to any of phi, that vanishes. So no contribution to Jacobian matrix. But now we have Jacobian matrix. For example, new contribution comes from this Ni exponential phi over summer voltage. This term is newly added, and since it has explicit dependence on phi II component, so now we have to have the additional contribution to Jacobian matrix of II, II component. Now we have this contribution. You can easily understand this is exactly the same term, and here we have minus summer voltage because we took the derivatives over phi. Okay, so previously, since we didn't have this term and this term and this term, our Jacobian matrix was just a fixed matrix. We don't have to recalculate it. However, now we have to recalculate it because when you change your phi, then your Jacobian matrix will change. So that is one point we have to keep in mind. Then now let's go to the pseudocode. So you can just define variables, and this is initial guess. This is initial guess. I just set certain potential over entire system. So well, is this good enough or not? Actually, this is not the best one, but for simplicity, we just use a constant initial guess or constant initial potential over the system. Well, if this really works, then everybody will happy, and if it does not work, then we have to find better way to set the initial potential. After that, now we learn the Newton iteration just 10 times. 10 is a magic number or not? So no, this is just arbitrary number. You can set the number, any number, and the Jacobian and residue construction shown in the previous slide, this, boundary condition and Laplacian part and charge part should be copy and pasted here. After that, now you have Jacobian matrix and residue vector, then you can calculate it. First calculate the update vector and just add your update vector to your solution vector, and now your updated phi will be used as the initial solution for next step. Then eventually you will have the converged solution and you can plot it. When we define the Jacobian matrix in this MATLAB example, I have assigned the sparse command instead of predefined zeros command. So, in MATLAB, if we have to have n by n null matrix, the default way or the first trial should be zeros of n comma n. So zeros, if you have zeros n comma n, internally the MATLAB or our system memorize n by n elements. So now we have a full component. But think about this one. You have a 3 by 3 matrix. Now you have a 3 by 3 matrix, and it has only 1, 1 component which has non-zero value, and all other components are actually 0. In this case, when you assign it as zeros 3, 3, then what will happen? In your memory, you will have 9 elements, and it will just read like 1, 0, 0, 0, 0, 0, 0, 0, 0. That will be the memory uses of this zeros implementation. However, we all understand instead of this just to write down all components in it, if our matrix is sparse, here sparse means that we have only a few or a small number of non-zero elements, and otherwise every element is 0 in user, then we can save a lot by saving, for example, 1, 1 equal to 1. For example, this is enough for specifying this entire matrix. So if we have a certain matrix, and if this is really sparse, then sometimes instead of specifying all of its elements, just specifying the components which are not 0 is more efficient to memorize it. That is the situation. So when you come back to our Jacobian matrix, and you can find that actually we are accessing only ii, ii minus 1 and ii, ii diagonal and ii plus 1. So for a certain law, which is Jacobian ii, something, actually we have only 3 non-zero elements. So at most, at most our non-zero element should be 3 times n. This is the upper limit of our non-zero elements. And you know the entire number of elements is n by n. So if we just calculate the ratio between non-zero element to the entire element, then this is non-zero and this is total. So you will have the ratio which is close to 3 over n. And when we go to a larger matrix, then this ratio will approach to number 0. It means that our system or our matrix becomes extremely sparse. So in this case, it is much more beneficial to have sparse implementation than this full matrix implementation. By default, matrix always assume the full matrix. Why don't you just do it together? Let's say, now let's just, clear all. Let me just repeat again. When we just set Jaco, then when you have a look at it, then each size is 0, 0 by 0. And now I want to say it's 1, 1 component is 1. Then how about this? In this case, we have 1, 1. And let me just add something. 5, 5. Then now it has 5 by 5 matrix, and it's 1, 1 and 5, 5 are 1 and all others are 0. And let me just have a look at it. Then its size is 5 by 5 and byte is of 200. Oh, 200. So why do we have 200? Each element takes 8 bytes, and here we have 5, 5. That's the reason why we have 200. Then let me define once again a sparse matrix. Let's call it as sparse. Sparse and 5, 5. Then let's have a look at A is size 5, 5 and its attribute is now sparse, and we have 64 bytes assigned to A. Oh, although this is just a 0 matrix, null matrix, but it is not 0. So anyway, in case of a JACO, Jacob matrix, since this is a full matrix, when we change our entries values, that does not change the bytes. However, let me just write down this one. When I assign A's 1, 1 component equal to 1, then now when you have a look at it, then it is this way. Then 5, 5. Then oh, now we have much more component in this A. Then let me add a little further. For example, 4, 4 equal to 2. Then what will happen? Then we have a certain number. No change. How about this one? 5, 3. Then we will have also this number. Then 1 equal to 1. So as you can see, actually the memory uses of sparse matrix is sometimes better and sometimes worse than this full implementation. However, this is corresponding to 5 by 5 matrix, and if we go to really large matrix like 100, 100 or 1000 or 1000 or 10,000 by 10,000, that is really beneficial to use sparse matrix. Actually, sparse matrix implementation has overhead for full matrix. So it is important to ensuring that your matrix is really a sparse. In the case of a full matrix implementation, you can just introduce just a continuous part of your memory. Then actually indexing is just given by just your position from the starting address. So that is quite simple. But if you introduce sparse matrix implementation, you have a certain overhead to managing your non-zero element. So if you introduce a really full matrix by using your sparse matrix implementation, that will be more costly than the full matrix implementation. Please do not try use the sparse matrix implementation in your full matrix. Then let's go to anyway the implementation here. As that this is just a copy and paste version and realized in the MATLAB, and now you can see that everything is identical, and the only difference is now here I explicitly write down Newton iteration. So let me just start our L8 script. Then now we have numbers starting from 1 to 8, and we have done the 10 iterations. After that, the plus statement gives us the solution for electrostatic potential. It looks almost the same as before. Okay, you can do it. Then let me just do certain exercise. Here we have update. Now update has some correction. Then how about this? Now let's try to find out the maximum component of update. So first take the absolute and take the maximum value. Then every time it will first print the Newton iteration and maximum absolute value of our update vector will be printed out. So if I'm doing correctly, then why don't you just do that? Oh, here you can see that starting from our 0.01, the initial, the first iteration gives us 0.01 as an update vector. The maximum update entry was about 10 to the minus 2. And you can see that now we have already in the second iteration, we have 2.7 times 10 to the minus 6. Oh, we have almost 4 orders of magnitude decrease in its magnitude. And after that, already in the third Newton iterations, we are quite close to the limitation of double precision number. And you can see that 10 to the minus 13, 15, 16. After that, you can find that this number is just saturated around 10 to the minus 16. So even at the end of our Newton procedure, still we have 10 to the minus 16. Then why don't you just introduce certain thing? If this number is, let's call it as error, and if error is smaller than 10 to the minus 10, so 0.1 nanovolt, then just to break this new loop, then what will happen? If our solution is sufficiently close to the real solution, then our update will be also very small. So we are now using the magnitude of update vector as an indicator of our closeness to the real solution. So when I run it once again, then only 3 Newton iteration is enough for our convergence, 10 to the minus 10 volt. Now let me wrap up this lecture. Since we have Korean Thanksgiving Day in this Wednesday, the due is next Monday, and just to write down the nonlinear Poisson equation solver by your own. And the only difference is now you have to use 0.8 nanometer, and in this example or in this lecture note, I have just applied it to Vg equal to 0 volt, but please try to do so for your gate bias from 0 volt to 1 volt. So maybe 1 volt will not directly accessible from this code. It will diverge. So please do not use this kind of crude initial guess. Instead of that, if you wanted to solve gate voltage equal to 0.1 volt, then please use the solution at 0.0 volt as an initial guess. Then you can solve it. After that, if you solve 0.1 volt, please use the solution, converged solution for 0.1 volt to the initial guess of your 0.2 volt. You can proceed step by step toward your final goal like 1 volt. I made a mistake. We have to write down in this way. Sorry about that, and I will change my actually I will change my lecture note when I upload it to our GitHub repository, but unfortunately our lecture 7.5 cannot be modified, so let me just leave a note in its description window. Let me wrap up today's lecture and enjoy your Thanksgiving holidays, and see you next Monday. Bye.